from the University of Paderborn in Germany in 2003. And after that, like, so he has extensive postdoc experience during 2004 to 2006. He worked at several places, extracting the flavor from each of these places, I guess. Like, so he has been FRC postdoctoral fellow in the Graduate School of Engineering at Osaka University, Japan. Then he was at Center for Optical Technologies in Lehigh University in USA. Then he was in the Integrated Optics Group in University of Paderborn, and also at a short time in Laboratory M. Cotton in a CNRS lab in France, Orsay. Right. So he joined as a faculty in IIT Madras in 2006, where he is now a full professor. So his interest, of course, is in nonlinear integrated photonics, and he's a pioneer in silicon photonics. So we're privileged to have him as our first speaker in this series. And yeah, he's new feather in his cap is he's heading the Center for Programmable Photonic Integrated Circuits and Systems, which is funded by MAITI. So this is a center in IIT Madras. So he's leading this activity, and we wish him all the success and look forward to a nice talk.
Okay. Yeah, thank you very much, Ben Gopal, for your introduction. Shall I start?
Yes, please.
Maybe I share. So, is it visible, my slide? Can you confirm?
Yes.
Ben? Yeah.
Yeah.
Okay.
We can
fine.
see.
Yes.
Yeah. Okay. So once again, thank you very much, and also I must congratulate IEEE Photonics Society to have Bombay chapters, and I'm really feeling honored to become the first speaker for this chapter. And thank you very much for inviting me, especially Professor Ben Gopal. And so for that purpose, I thought that because of wide audience, I thought of talking something bit of broad aspects of silicon photonics technology and its progress, and some recent applications. And for that purpose, I think already he has introduced, but in a nutshell, I just put up here my research profile so that you will be understanding what I'm doing and what I'm going for. Since 1996 to 2006, almost 10 years, I was working in lithium niobate integrated optics and several institutes, starting from IIT Kharagpur, already mentioned Benigopal. And then 2006 onwards, silicon integrated photonics, starting from the scratch at IIT Madras. And in course of time, we had developed a few labs and centers. First of all, in 2000 itself, we started building integrated optoelectronics lab. And then 2012 onwards, I was one of the founding member of Center for NEMS and Nanophotonics, and now also in NETRA project, second phase running. And very recently, this is the Center of Excellence, CPIX, Center for Programmable Photonic Integrated Circuits and Systems, and with a lot of commitment for next 5 years. So we have commitment for developing so-called FPGA core technology, so-called Field Programmable Photonic Gate Array. And we are in a process of developing, we have committed for developing 3 products in 3 sectors to be useful. And then startup plan, etc. And also we have a industry collaborator who will be working for system in package for silicon photonics chips, SI2 Microsystem, Bangalore. The faculty team for this center, actually myself, here it is shown, I am working silicon photonics area, design, fabrication, testing, all area we are covering here. And also we have a senior faculty member, Professor Enakshi Bhattacharya, who is actually expert in MEMS and microelectronics. Janaki Raman, Professor Janaki Raman, he is expert in integrated circuit, electronic circuit aspects he will be looking in this project. in the center. And then Deepa Venkatesh, she has a very good lab, system level fiber optic communication lab. I think one of the best lab in the country. And then Professor Anil Pravakar, long time he's involved in quantum photonics fiber optics, different QKD systems. And then Professor Nandita Dasgupta, Amitabh Dasgupta, both are expert in microelectronics and devices, microelectronics process. And then Professor Christopher, who was the former DRDO chair, now our colleague. He is actually playing a pivotal role, just industry academic collaboration, interactions, he is helping in this direction. So this is the core team of the entire silicon photonics research activities now happening in IIT Madras. And with that, also we have plenty of research scholar, project staffs, project officers are there. Solomon here, he is actually currently Chief Technology Officer for the CPICS, recently employed and started working. And then so many research scholars are there, more than 10 PhD research scholars, MS research scholar, and project staffs all involved. And though they are not stationed here in lab in IIT Madras because of lockdown, but regularly we are remotely working and interacting. And in principle, all of them are very much involved working from home. So now for today's presentation, as I mentioned, that I would like to give some kind of overview what is happening around the world and what we are doing, where we are compared to whole world internationally. So for that purpose, I wanted to give a little bit of introduction, background story, just to give you some flavor how this silicon photonics technology came into picture. Okay, how it is evolved. That I will be giving in the first section, just overview. And then this CMOS compatible silicon photonics. So what is that CMOS compatible silicon photonics, and how it is becoming mature to have certain industrial product, something like transceiver, high-speed transceiver for optical interconnect applications. And then beyond optical interconnect, what other area coming up for silicon photonics, that I will be covering also. And towards the end, I'll just try to give some kind of very quickly overview of silicon photonics research at IIT Madras recent progress. So first, as I said, that I will be giving some overview on introduction to silicon photonics, the background story. So here, just if you just look at today's silicon photonics technology, I just observed my personal observation here. I summarized as a whole. You see, today we have a product from Intel, 100 Gbps transceiver, and millions of such transceivers being actually sold every year. Okay, that is the first silicon photonics product from Intel, and that happened after 16 years of research and investment. So they've started around 2000, and then around 2016 they had a prototype, and since 2018 they have full-fledged products, and they are actually exporting. And then Luxtera, another company, they have been involved in silicon photonics startup since 2000. And they together with TSMC Taiwan, they developed the photonics CMOS compatible photonics technology, and that is the best ever so far. And they demonstrated 4 Gbps transceiver, and that finally it is acquired by Cisco recently. And if you see, it is now product available, first product, but historically, if you see, it is a story of 20 years, starting from 2000, but before that, a lot of research was going on academically. And I have tried to search, just a Google Scholar search, integrated photonics, actually. If you just search 2001 to every year, if you see number of publications, article, you get this exponentially growing. Started in 2000, only 590. Before that, mostly academics, laboratory, like institute, universities, they were doing research since 2001. It is now industry subject, and it is growing, and up to 5,820. It is reported into 2020. And if you, when I search integrated photonics, actually it means some kind of some standalone devices, not all based on silicon. There are some other integrated optics platforms also is counted here. But when I search photonic integrated circuits, this is mainly silicon photonics. Okay, so for that, if I search again from 2001, you see it was 2001 about 15,400 and a little bit higher about 17,000 next year. And then it is more or less flat till now. So this, I was a little bit wondering that it is so much hot topic and so much prospects and the products are coming up, but this research is almost flat. Flat means it is basically publishing, but it is not growing like exponential like this. I think it is my personal observation could be because the but silicon photonics research, it is a very expensive, sophisticated technology, lab ambience you need, investment also you need. And because of that, whoever already have already developed, they had the good laboratory, they are only involved for photonic integrated circuits. But I think those who are developing labs, they are actually still belong to this integrated photonics. That means individual components, one or two components, integration, everything they are doing, and they are falling in this category. That's why it is growing here. So I think so far until 2020, so only this transceiver markets and transceiver related research, optical interconnect related research was going on, and investment in the industry also in that particular product. But very recently now, many other area opened because technology is now mature. Optical interconnect technology is almost solved. It can be improved, of course. But based on that technology, it is a scalable technology. People are just exploring many other area. I have just documented here that other area means, of course, including optical interconnect, high performance computing, and reconfigurable high-speed transceivers. That is the two-thing computing and transceiver. This is the two thing. These products are available, but this area it is under development. Many industry involves. I think some high-end computing systems also they are using silicon photonics. Apart from that, some advanced civil radar system, avionics. It's basically microwave photonics purpose. Silicon photonics also being projected, and a lot of academic interest and a lot of defense laboratories across countries, they are investing, and high-end devices, circuits they are developing, but no product so far. Sorry, I'm sorry for that. But it is anytime it will be launched. And then another area is lab on chip, chemical and biomedical sensing purpose. And of course, as it scalable integrations, everything happened, people are talking, and high performance computing we are talking, then neural networks, artificial intelligence purpose also, it is highly potential, highly important. And again, 5G communication and Internet of Things, so it's a part of microwave photonics technology that is also people are projecting for 5G communication, 6G communication, or etc. And then, you know, this is the latest hype, you know, quantum computer, quantum logic gates. People are using superconducting nanowires and superconducting qubits for computation, etc. But, you know, those are not very much scalable. But if you use photon as a qubit and silicon photonics as a platform, then there is a high chance that you can actually demonstrate a scalable quantum photonic processor and quantum key distribution chip, QKD chip. The overall quantum information processing is possible. So till now, up till 2020, the market search shows that it's a only transceiver market is about 1 billion as stands today. Now, after including all these things together along with the transceiver markets growing, it is expected that by 2025, it will be about 3 billion market. So now I'll be just discussing about something, how the silicon photonics technology evolved. Again, it is uh, it is the it is not that it is standalone independently. All of a sudden, silicon photonics started growing. It is not like that. It was actually it is evolved because of the some kind of shortcoming, some kind of bottleneck in the electronic industry. Okay, that's why I wanted to give where is that a bottleneck and how their silicon photonics came in as a survivor, and a lot of investment came in. I will just give a couple of slides. I will spare for giving you a clear picture. So 1947-48, transistor was invented. Started actually 1947 December, and then a couple of other paper came in 1948. And Shockley, Bratton, and Bardeen in Bell Labs, they demonstrated first germanium transistor. Looks like this. It is in the order of 1 centimeter and so on. And so that is why this transistor later on, because of the scaling, etc. Now a lot of success came in. That's why after 50 years, similar device again fabricated by Bell Labs, and it is displayed here. So later on, once transistor was demonstrated, just within a decade or so, people proposed and demonstrated integrated electronic circuit. First time in 1959 by Jack Kilby. So he just got a patent. He was working for Texas Instruments, patent for miniaturized electronic circuit. That time integrated circuit was not mentioned in the first patent. And in the germanium, he could integrate 3 different transistors. And you see this is how dirty it is, the first transistor, and a lot of wire connections, everything here. And after a couple of years later, because germanium has a lot of problem as a material aspects and also device aspects, people were looking for some alternative, and then silicon came in, and Robert Noyce got a first patent for IC, integrated circuit. That time actually patent as a integrated circuit came in. He was working for Fairchild Semiconductor, and here 4 transistors were integrated, and you see these white lines, all these are metal interconnects. So it is specifically metal interconnect. So you don't need external wires, etc. Inside, if you have a transistor, you can interconnect them. That can be also fabricated with a photolithography, the lithography technique. If you can develop that, that was actually demonstrated with a lot of hope. And as went on, then you see more and more transistor you integrate, then you can get a lot of functionalities, computation to a lot of logic gate operations, etc. And people started working, and also since it is industry, Texas Instruments, Fairchild Semiconductor, etc. They have invested a lot of money, just thinking a lot of potential. And Gordon Moore, who was actually working for co-founder of Fairchild Semiconductor. Yes, some echo is coming. Okay, so he wrote a paper in 1965. The paper title is "Cramming More Components onto Integrated Circuits." Based on the data, people started integrating more and more transistors, and based on that data and the cost, fabrication cost, etc., he plotted 3 graph here. 3 curve, if you see, 1962, 1965, and proposed curve for 1970 is shown here. So here, x-axis, you see number of components per integrated circuit, per chip, you can say, and then relative manufacturing cost per component, the y-axis. Okay, so this is the manufacturing. You can just some scale is given. You can consider that is a dollar, US dollar. You can consider, and this is the number of components. As you see, 1962. You see, initially, if you keep on increasing the number of components up to say 10, cost is reducing. Then if you try to integrate more than that, you need better technology. That's why cost is actually increasing. So it is something like that. Up to 10 number of transistor you could integrate, which is cost effective. You cannot integrate more than that. It will be, you can, but cost will be higher. In 1965, the year it was published, it is showing that you could go up to 100, more or less 100, with a cost effective, and overall cost is reducing, but this is the best optimum number you could integrate with a minimum price. And 1970 predicted that it could be about 1,000 or so. So this is how he plotted that just looking into this number, this optimum number, cost and optimum number, maximum number you can optimized number you can integrate, and he plotted starting from 1959 and so on. He was having 4 data that time, and predicted that every 24 months you can double the number of transistors uh, with a cost effective way. Okay, and later on that was revised as a, it is not 24 months, it's 18 months, it was revised later on. And now this is the report in 2018 from Semiconductor Industry Market Survey, and I found it in NVIDIA website. And that is what it says, that starting from 1970, when it was first time IC was proposed, and if you go for until 2018, 2 years back, so you see different, these are very, I'm sorry that this cannot be readable, but these are basically model number of different type of processor, microprocessor units, and different type of computer processor, you can say. Okay, so as different company, they came up with a different type of processor. And here, y-axis, it is showing number of transistor count in the processor. So if you see around 2018, there are many products available where the number of transistor is close to 50 billion. 50 billion transistor could be integrated in a microprocessor for computing purpose, whatever you are using, CPU, graphical processor unit, all those things you are till date using. And recently, actually, NVIDIA P100 GPU they are using, fabricated from TSMC, that is actually 92 billion transistors could be integrated. But thing is that that has been possible because of the advancement of technology. Transistor size is reducing. So transistor size is reducing so that you can integrate more number of transistor in a smaller footprint, and you can interconnect them internally with a metal interconnect. However, as the transistor size keeps on decreasing, your interconnect dimension also decreases. So here is one model estimated. It's schematically it is shown that the x-axis shows the technology node. Technology node means it is shown micrometer. It's a 0.65 micrometer. Very early days, 1980s or so. That's a 650 nanometer technology was there. That means transistor size could be 650 nanometer. If it is a MOSFET, it's a source to drain or gate length, that is actually the transistor size, you can say. So as the time goes on and advanced technology comes invented, so here it is shown about 90 nanometer technology. Today, of course, people are talking about less than 25 nanometer, even 7 nanometer technology available. So as the technology advancement goes on, your transistor size reduces. That's why gate delay means your input, if you are giving an input signal to the gate, source to drain, or input to output, if you just measure that delay, time delay, that actually linearly decreases because of the size reduction. However, whenever you are interconnecting one transistor to another transistor with some kind of metal interconnect, that because of the scaling, their cross section reduces. That's why resistance increases, and also density of interconnect also increases. And because of the increased density, you can see some kind of, if one
Hello, Vijay, are you there? Like,
yes, can you hear me?
yes, we're
Oh,
back. Yes.
somehow I was mute. I don't know how. So where how long I was off?
Just for a few seconds.
Okay, fine. So
sorry to interrupt, sir. Can you please use the ledger Laser pointer.
Can I use laser pointer? Okay, let me see.
Sir, pointer options.
Yeah. I'm just getting there. Yeah, sorry. Thank you. I'm sorry. Thank you very much for that. So you see the gate delay is actually decreasing because of the transistor dimension is reduced. However, as I said that this interconnect cross section is reducing, that means resistance will be increasing. And then density of interconnect also has to go up because of the more density of transistors. And then there's some fringing fields that will create some fringing capacitance. So RC constant will be increased. So delay due to interconnect, for example, copper and surrounded by low K, that means it is a kind of transmission line. So if you see copper interconnect, just this curve, then you will see that it's increasing. So after 180 nanometer technology, some different slope. This is because some kind of quantum effects comes into picture. That's why this delay again increases. So if you see together this gate delay and interconnect delay, if you add them together to get a figure of merit, so that overall delay, that is how it will matter for the speed of a integrated circuit. If you see that up to 180 nanometer technology, it was actually coming down. Delay was coming down so that you could switch on and off, faster operation could be possible. It's a decreasing, and that means speed is increasing, and beyond that it is started to grow. So that means delay, even though you can integrate more number of transistor, manufacturing cost reduces, but the speed you are not gaining according to your according to your expectation. So that is the limitation. That is the bottleneck. That is the physics limitation for the physics. So you can't do anything with the technology. So that's why this is called electrical interconnect bottleneck. So people were afraid because of this, because the Moore's law till now, it was predicted that every 18 months it will be doubled. And because of this reason, you cannot really follow that path. So people started saying that maybe probably that Moore's law, end of the Moore's law, something like that. They were predicting, and they were trying to go for some alternating solution. So one of the solution already achieved, that is that, you see, whenever more number of transistors are there, this layer you have all the transistors. So you can connect your neighboring transistor maybe with a smaller cross section of the interconnect. But whenever you want to connect from a transistor a little bit relatively remote distance, maybe a few hundred microns or so, you can take a via and you can increase the cross section vertically, three-dimensional vertical. These are all dielectrics. Use the via, and then you can use another metal layer, interconnect layer, which is having higher cross section, and their density can be lower. So that is intermediate interconnect. That is how you can gain some kind of bandwidth. And if you go for a little bit more than that, few millimeters or so, then you can again increase the cross section through a via, and that is another metal layer. And then you can connect to another location, group of cluster of transistor, then you can gain that can be higher speed. So that is how it is managing. Wherever necessary, you just increase the interconnect cross section by giving allowing some via vertically, and then another layer of things. In this way, people gone up to 7 to 9 metallic layers so far. But still, demand of speed is more coming more and more internet traffic, all those type of things, as you know, always you want higher speed. So thing is that here people try to see how far we can go vertically, 7 layers, 9 layers, and so on. Can we go up to 100 or so? Technologically, though it is difficult, but still, theoretically, it is found that it is calculated. If you just see that two different interconnect length, it was considered. One is about 5 millimeter, another is 3 millimeter. So this is actually 3 millimeter, and this is 5 millimeter. And this is the feature size of the transistor, or you can say here feature size of the interconnect, basically cross section. So you know the feature size actually increasing means your gate delay is supposed to be increasing. That is what it is shown. Gate delay will be increasing, but you are not, your gate dimension it is smaller, but feature size of your interconnect you are increasing in this direction. So this two interconnect length, the delay you see calculated delay for 5 millimeter and 3 millimeter is reducing as you increase your cross section. But as you keep on increasing 1.5 micron, 2 micron, and slowly it is getting saturated. So after certain increase of cross section of the interconnect, you are not really gaining the delay. So that is somewhat calculated the phase velocity, any signal you are sending through that interconnect. The phase velocity actually is saturated at exactly around c by 6 is the velocity of light. So again, you know, that is the transmission line. Transmission line, it depends on what frequency you are operating. The frequency, it has to be designed to operate at certain frequency, dielectric, all those type of things are there. So bandwidth limited. So that's again, this is another reason the interconnect bottleneck why it is famously known. So what is the alternative? Alternative was that, you see, this is the another alternative. I get this is a very nice review paper here. It is showing that it is industry is following that you can, instead of all the transistor in the same layer, you go for vertically 3-4 layers of transistors, similar to metal layers also. First layer you can have a microprocessor, then you can have a via metal layer you can use, and then this transistor layers doing all this processor logic, gate operations, everything will be doing computation, all those type of thing. And then the next layer of transistor, that will be just a memory. One transistor means 1 bit memory. And then again via you take wherever the metal interconnects, it's a higher cross section you are using, and that higher cross section also is not enough, then you take the signal out and give a feedback to another layer of transistor, which actually acts just to convert electrical signal into optical signal. So once you get an optical signal, then you can use your standard optical waveguide, which actually works based on total internal reflection. And that is how basically the fiber optic communication in 1980s and 90s, actually it's a kind of success came in, and we got the internet, high-speed internet around 1990s. But thing is that for it was economy at that time for fiber, long haul fiber optic communication. Low loss fiber were available, and you want to bundle all the data together for sending data actually one side of the world to another side. You can send thousands of kilometers, that's fine. But thing is that when you just think about, okay, same thing if you want to do within the chip, for example, or just chip to chip with short distance, or maybe rack to rack, board to board, if you just do, that was not that time too much economic. So still people were struggling what could be the alternative solution. And this was the actual model people just thought, well, if you can have laser and you have an optical modulator on chip, then electrical logic cell data and electronic driver, everything, you can drive that signal. Then optical modulator can convert electrical signal into optical signal, and you have an optical waveguide inside the chip again. If you can accommodate that fabrication wise, technology wise, then this is, instead of fiber, you have a waveguide, planar waveguide. Planar circuit you can design, optical waveguide circuit you can design, and then you can process optically. Process means you can do some kind of noise reduction or multiplexing, demultiplexing, filtering, all sorts of things you can do. And then finally, you can, wherever necessary, you can convert back the optical signal into electrical signal and feed into another electrical logic cells. So in that case, you don't need this cross-section, interconnect cross-section enhancement, and you don't need to bother about bandwidth limitation of the electrical interconnect. Optical interconnects means velocity is c, frequency, you can, if you are using third generation of optical communication window, that is 1550 nanometer, around 195 terahertz. So carrier frequency is very high, so you can enjoy huge bandwidth. Bandwidth would not be an issue. And multiplexing, demultiplexing, all those type of things play a major role. So that was the target. However, this thing, it's a simple, straightforward idea, but could not be implemented because of the lack of technology. So that you can co-integrate photonics and electronics together, people started exploring that silicon on insulator wafer, that time commercially available around 1995 or so, that time. And that was manufactured and more and more for CMOS electronics. CMOS electronics was at that time demand that because of the bulk silicon has a lot of latching effects, leakage effect, power consumption effect is there. So electronic circuits was being actually fabricated in silicon on insulator. What is that actually? You have a silicon layer, thin layer, and you have box layer, and you have a substrate. So in this layer, silicon layer, so-called silicon on insulator layer, all the electronics will be there. And to isolate one circuit to one transistor to another circuit transistor on demand, you can just etch the device layer, then it is oxide, and you could isolate, and leakage current, everything could be minimized. But at the same time, people started to exploring that, oh, this is silicon, and silicon, if you have, it is a pure silicon, if it is intrinsic, not doped, then at 1550 nanometer, that is like a dielectric. It is completely transparent. So that silicon on insulator can be utilized as a 1D optical waveguide. If you do a little bit of lithography and etching, etc., then you can make this type of cross section, and then you can have a waveguide. Surrounding oxide that can act as a heater, a cladding. And on the top of that, if you have a micro heater, just metal micro heater, if you heat a bit, silicon is a very good thermo-optic material. So you can change the refractive index. You can actually tune the silicon waveguide devices. So you can have a waveguide devices, you can have a transistor silicon, and you can have a modulator. How that is possible? You have a waveguide both side. If you dope p-type and n-type, then if you just control a bias, it is a PIN structure. Intrinsic region, your optical mode will be sitting, and p side, p doping this side and n doping this side. Then if you just control the bias, then you can actually control the carrier, phi carrier inside the waveguide region, core region. By controlling the carrier, you can change the absorption, you can change the real part of the refractive index, and that is how you can get a phase modulation. And phase modulation is there means you can get an intensity modulation by incorporating Mach Zehnder configuration. And of course, if you are using 1550 nanometer, that is transparent in silicon, but you can have a silicon germanium, which is also CMOS compatible. Silicon germanium band gap is lower, and you can actually detect 1550 nanometer. So that photo detector, that means electrical signal can be converted back into, optical signal can be converted back into electrical signal by means of photo detector. And silicon is an indirect bandgap semiconductor. Normally, it is very difficult. It is not at all possible so far to integrate laser diode. So people thought that, well, laser diode can be off chip. You can have a grating coupler. You can bring fiber, and you can couple light, and you can do all the processing inside. So, a computer, for example, if you want to use this type of microprocessor and optical interconnector, etc., you can have a laser that can be sitting outside. You can take a fiber and you can launch it, and all the things you can do. So based on that, that was the idea, technology being developed around 2000. And when industry wanted to go for it, they wanted to estimate whether that is profitable or not. All this idea, everything is fine, but you need to see whether it is really give you some profit. So here is a Intel Technical Journal estimation they published in 2004. They calculated around that time, whatever laser available, whatever fiber available, whatever getting coupler available, whatever waveguide loss available, based on that, they calculated that if a typical silicon chip length is 17.6 millimeter, about 1.76 centimeter, if it is a typical length, and if this is the x-axis is considered as a length 10 to the power 0, that means normalized length. 10 to the 0 means 1. That means it meant for actually one edge to another edge of the chip length. Okay, and they have calculated 3 different parameter figure of merits: delay, power, and bandwidth. And they found that as from starting from 2004, and they just extrapolated the technology, etc., how it will be coming up, and they found that for example, this bandwidth you will be getting gain by 2007, that up to this length you can have electrical interconnect. It's good enough, economy enough. If you want to go beyond that, you better go for, so this is the curve. If you are going more than that length, then you should go for optical interconnect. That means you need to have a modulator laser and waveguide then it will be profitable bandwidth wise. And this is actually similarly, it is for power and this is for delay. All those type of they have calculated. That means they estimated that within the chip, wherever necessary to go for beyond, say, for example, few millimeter, it is better to convert electrical signal into optical signal, process it optically partly, and then you convert back into electrical signal, then it will be economic. It's a cost effective. So once they are done this estimation, they invested a huge amount for silicon photons technologies, and IBM also started working on that, and they actually developed and the silicon photonics devices, all the optical interconnectors like modulator, multiplexer, demultiplexer, photodetector, everything using their 90 nanometer CMOS technology node. Here are some example. Modulator, they have demonstrated 25 Gbps and photodetector up to 20 gigahertz, and WDM filter, 4-channel WDM filter, and then it is shown all the components like a metal, that's a waveguide structures, everything. All of them were fabricated based on the CMOS process line. You know, CMOS process lines in CMOS foundry, they fabricated this. That means that they have not modified any process related equipment. Using same process equipment, whatever they used for silicon electronics, same process line, same facility they could use to demonstrate optical interconnects in silicon. So that actually presented in 2012, and then later on, after 3 years, actually it's a famous paper and published in Nature, and where actually it was shown that the processor, where RISC-V processor, memory, and transceiver, everything was co-integrated in silicon using CMOS technology, and you could actually communicate. So one particular chip to another chip in between. This is one chip, memory mode, and this is the processor mode. That means you can processor to memory, you can communicate in between. You have a laser external and some fiber optical amplifier outside. So that was actually a landmark paper where this type of chip, where actually electronics and optics together co-integrated. You know, electronics, you can think of billions of transistors are there, but for photonics purpose, they say that 850 photonic devices and 2 into 11, that means 22 electro-optic transceivers, they integrated along with 70 million transistors to communicate. And communicate means this electronics they could control by FPGA, field programmable gate array, and they could transmit video data from one processor to another and store that video, and they could again outstream that video. So that was actually available still in the internet available if you want to see. The same chip they have used, and whatever they got, the video streaming, etc., that is available in the internet. So far this thing, after this, people were looking for some products. So 2002, 2020, all the research, industry level research, actually result into this products, as I mentioned in the beginning of my talk, that 100 Gbps transceiver, 400 Gbps transceiver, and they were heavily used in data centers. Data centers, basically all these Facebook, Google, all those, they in that data center rack to rack communication, they used to normally initially they were using copper cables, and they started replacing this thing just to reduce the power consumption. Okay, this is some market. We have seen different market, how passive photonic filters market about 25%, transceiver market 85%, 35%. And then it is a projection of up to 20, what was it in 2019 in India, Australia, Japan. Also, I see that people are also, it is very difficult to get Indian market study, etc. But nowadays, all the market researcher, they are documenting what is the prospect of being in India also for silicon photonics. What was in 2019 and what would be in 2026 with respect to other countries like Australia, Japan, China, such a Asia specific countries comparison. So I have just given some kind of silicon photonics, how it is evolved, where because of the electrical interconnect bottleneck, silicon photonics came in, and up to the product level it is reached, and that is the market as of now. Now I will be talking what is there for silicon photonics beyond optical interconnect. So beyond optical interconnect, as I said, that this is a microwave photonics. So microwave photonics, you know, nowadays people are for all this RF microwave, they are looking for higher and higher frequencies, X band and K band, Q band, all those type of things. People are going up to 26 gigahertz and so on for 5G, 6G communications. So they are normally electronics and all the microwave circuits, they are becoming bulky and a little bit of expensive to operate at that frequencies. So people are thinking that why something optics and silicon photonics, so the technology is matured now for transceiver industry. So same technology you can use for microwave photonics purpose. How that can be done? You just have your all the signal coming in. You just use a modulator laser source so that all the signal you convert into optical signal, encode into optical signal, and you process optically just to reduce the electronics load. Okay, so then you can again you are up converting and then down convert again and to get your RF output for your receiver. So this is another huge market coming up, particularly in defense strategic market. It's a very good, and also aviation market, avionics industry, everything people are also looking for. And so far, a lot of good products are, a lot of good prototype devices are coming, but I think product in the market will be coming very soon, I suppose. And then another thing is that, you know, there are many local area networks are nowadays coming out, like fiber to the home, fiber to the office, all those type of things. Sometimes you may need just within a room, you need some kind of switching network, because you will have so many devices, so many equipment will be there, so that you may need 1064 by 1064 switching network input to output. So that type of switching network also you can fabricate in silicon on chip switching. Okay, no other platform can give you that type of switching fabric. So this type of industry also coming out for switching fabric purpose. So you have different server and inside the server transformer, their silicon photonics will be there, and also switching network also, fiber coming in and then signal coming in, and you can route one place to another place. That is also another things are coming. And lab on chip for biosensing application. I think this is something well studied in different material platform, starting from glass to lithium niobate, polymer, many other components, because low cost, all those type of things till now people are doing. But as you know, silicon photonics foundry itself is coming mature, and fabrication cost is reducing. So slowly people are moving from other integrated optics platform to silicon photonics platform, where you can actually just light source, you can maybe hybrid 3-5 semiconductor laser source, you can just flip chip bond, and then you can have a silicon waveguides, and then you can have a microfluidic channel functionalization layer for detecting biomolecules, etc. And also you will have on-chip detectors as well, and you can have on-chip electronics also for readout. So it can be completely lab on chip biosensing application. Silicon photonics things are coming. So so far in academic university, people are demonstrating small component for sensing application, but for industry purpose, you need to think about the circuit, entire circuit, both co-integration of electronics, optics, microfluidics, and sometimes 3-5 heterogeneous integration. All peripheral fringing technologies are coming in to go for a complex products. And then, as I said, the quantum. So integrated quantum photonic processor, that is actually a huge thing coming, and at least one or two startups are there, and they are promising that within 2 years they can actually they will be coming up with a silicon photonics quantum computer. Photon will be used as a qubit, and you can use a multiple, maybe thousands of qubit. You can actually qubit source you can generate, and you can do all sorts of quantum mechanical quantum photonic interference, all the logic gates, Hamadat operation, all those type of things you can perform using so-called linear combination of quantum, I think linear quantum computation, some abbreviation I'm forgetting that particular, that means linear operation. All this linear operation you can get of the for the qubit using classical devices like Mach Zehnder interferometer, splitters, same classical photonic circuit you can do, and all the linear operation you can do for qubit. photonic qubit. And then, another important things are coming. So, so far, if you consider your transceiver or quantum photonics things, chip, or you can consider lab on chip, microwave photonics, everything, they are, people are trying, industry also trying one chip, one specific application. So application specific photonic integrated circuit being developed so far. Now you know what happened to electronics industry. Initially ASIC, application specific integrated circuits were there. One particular circuit, chip, it's dedicated for particular function. Then people see that, okay, some little bit modification, you can program that circuit to other application also. That's why it came like a FPGA, field programmable gate array. So along with ASIC, FPGA together actually capturing whole lot of computer industry and electronics industry. So people are now trying that, okay, similar idea, if it can be translated into photonics also. Photonics so far, similar to ASIC, it is ASPIC, application specific photonic integrated circuit. And if you can have a some part also programmable, field programmable photonic gate array, if you have, then together you can actually get more cost effective and more functional chip. Same chip you can reconfigure or program for various applications. So this is one typical chip, photonics chip, waveguide, particularly Mach zehnder interferometer arranged in a particular manner, particular mesh structure. It is hexagonal structures here. Along with that, some high-end ASPIC, application-specific photonic integrated circuit, like delay lines, filters, all those type of things in surrounding region you can have, and you can have also RF input-output you can have. And this type of chip, if you just put in a system in package, that means photonics chip, and you have a control electronics, and all the laser can be outside, and RF input output will be there, and you can have some kind of USB type or Ethernet type connections to the computer through which you can actually program. And same chip you can use for different application. You can, one day you will see that, okay, this chip now it is programmed for operation in the area of microwave photonics, and same chip, if you do a little bit modification, you can use also for quantum photonic processing, certain quantum key distribution, etc. You can do that. That has been in the idea level, and a lot of components being developed, and also some startups also already came up in European Union, and we are also working in this particular direction. Particularly our CPIC, Center for Programmable Photonic Integrated Circuits, targeting these things also. So this is because internationally it is also in a beginning stage, and we are also starting. Hopefully we'll be, one day we'll be competing internationally through this center. So this is our entire thing, entire picture for silicon photonics, and where we are, we can go. And I would like to take you through a little bit about our recent research, which is actually enabler for this center or for programmable photonic circuit. So you see, this is something, the Mach zehnder, tunable Mach zehnder integrated with 6 different phase shifters, and you can program it. This 6 different phase shifter, you can program it, and you can actually, according to your desire, according to your requirement, you can get signal, some signal in the cross port, bar port, and a drop port, and also switching purpose. This is something broadband. For example, in this case, it is demonstrated that C band and L band you can separate completely, broadband, and no loss. You see flat top here. So this is the device we can program for switching C band and L band, or demultiplexing C band and L band. And the little bit of variant of this you can use in this type of structure. I said that this is the hexagonal mesh structure. If you see one of the hexagonal, this arm, that is actually nothing but this type of Mach zehnder interferometer. So this Mach zehnder interferometer we have demonstrated, and it could be programmed. And along with that, we have also have some kind of ring resonator. Sometimes ring resonator can be also used as a programmable element in the FPGA circuit. So we have also demonstrated that thing, and we could program it for nonlinear photonic applications, where actually quantum qubit can be generated, and they can be filtered, separated, and take it to through some Mach-Zehnder interferometer circuit for linear operation, linear quantum photonic operations. So these things also we demonstrated, and it was actually highly cited, and good journal STQ we published 2 papers back to back. And along with that, I just, because it is IEEE Photonics Society Bombay chapter, I always grateful to Samir Mumbai. I saw that Anuj is also in the audience. So with his help, we very beginning in 2012, we started silicon photonics device fabrication in-house in IIT Madras, and that chip was actually packaged in Samir Mumbai, and Anuj actually helped that time, and we could fabricate this thing. And right now, I guess that the present generation of silicon photonics chips, this type of packaging is not useful. That's why we are collaborating with another industry, SI2 Microsystem, Bangalore. They have a very good facility for electronics packaging, and they are collaborating with us to develop silicon photonics chip packaging purpose, so that we can go for system in package. So with this, I just put up this particular structure. So whole world is now silicon photonics industry actually trying to optimize this structure, this simple structure, Mach-Zehnder interferometer structure, with different position. At least here it is shown 6 different phase shifters are there, and you have to program this phase shifter effectively so that you can get certain desired output, 2 by 2 output, and then you can get a mesh structure. The challenge is that power consumption, crosstalk, footprint. So all these things are now challenged so that you can scale it up and you can integrate more number of such tunable building block. And people are also trying to get some kind of phase shifter, like a thermoptic phase shifter, as well as like a plasma dispersion phase shifter, and also recent trend is something called phase change material, also like a GST, IST, this type of material people are using. So where you can get some kind of non-volatile memory type application. So you need only need a pulse, just particular pulse for short duration, then your phase will be changed and your refractive index change will be permanently happening. So in that case, your power consumption will be only that duration, switching duration only. Okay, so that type of things, research area is coming out, and we will be looking forward for that. With this, I just thank you very much. Hope I could give you some flavor. I could not go much depth because maybe there are wide audience, but I would be happy if you have a couple of questions. I would be happy to answer. Thank you very much.
That's a wonderful talk, Vijay. Like, so it's really informative for the students and the beginners. Like, so it gives about the opportunities and what we can do in the country now, right?
Yes.
So there are a couple of questions. The first one was by Gaurav Bharati. So he's asking, like, so which device is used as a phase shifter in your MZI structure? Is ring resonator used?
So here, here, if you see, we are using a micro heater. So the titanium metal, it is deposited just outside the waveguide ring. So then you pass current, and then because of Joule heating, temperature of this portion of the waveguide will be changed. And silicon is a good thermoptic material. So you can get 1 degree temperature change, means in the order of 10 to the minus 4 refractive index change. So that is how you see here, particularly I have not explained in details. This type of device, if you work in a higher power, hysteresis type transmission characteristics you will see. In transmission, if you see, if you just go in the forward direction, transmission will be like this. And reverse direction, transmission will be like this. That means reverse direction, it can hold more energy. And that time non-linearity will be there, and you can get more efficient quantum so-called Fourier mixing, or so-called entangled photon pair generation will be happened. So that is how we have used here for our ring resonator. So it is basically micro heater. There are other options are there, but we are using right now micro heaters. We are exploring some better. Here power consumption is a little bit higher. That's it.
Thank you. Yes, so there is one question from Deepika Verma. So she's asking, like, what is the effect of increase in slab height on the confinement factor and effective mode area in case of rib waveguide?
Yeah, so that's a good question. I don't have relevant picture. I think maybe who is asking question he knows, but I thought of one good picture would be helpful for others. So you see, waveguide structure, you have a slab silicon. I think I have the first slide. I can help there. Yeah, here. So if you see this, you are talking about this type of waveguide structure. You have a reeve here, waveguide will be confined here, and this is the slab height. So you see, normally this slab is kept here so that in the slab region you can dope, p-type doping or n-type doping for modulator purpose. Otherwise, you don't need to keep this slab region. You can have this type of waveguide region. The advantage of not having slab is light will be confined tightly. Tighter modal confinement helps you to bend the waveguide structure tightly. You can make a very 5 micrometer reading radius also. Ring resonator, if you want to design, you can have a 5 micrometer also. But whenever you are using this type of structure, a mode will be little bit extended towards the slab region. So when it is extended towards the slab region, bending loss will be more. So that's why you will not be able to bend very tightly. So that is the trade-off. But what you can do slowly, wherever you need a sharper bend, you can use this type of waveguide. Wherever you need this type of waveguide structure, there we have that technology also, that type of PDK available also. I think that should not be an issue. Whatever design you want, for what purpose you can use. But the bottleneck is that the bending loss. Bending loss is very important. And also, as you said, that effective area, because slab, if you are using, your effective area will be large. Larger effective area means for nonlinear purpose, for example, quantum photonic application purpose, you need more pump power. So that also you have to think. There are many other issues also there, not only the effective area, you have to see the dispersion also. So dispersion also play a major role for quantum photonic application or other applications also. Hope I could answer there.
Thank you. So there is Rohin Y. Like so, his question is like, what are your views on IR Labs claims on low power optical I/O technology?
Yeah. So I think I'm closely following this IR lab also. I think they are very good. Actually, they have a very good tie-up with the global foundries. Global foundries actually they almost want to launch a very good PDK for so-called in silicon, bulk silicon, where actually you can co-integrate electronics and photonics. So far, co-integration product is very rare. But Global Foundry has they have acquired this IBM technology, and then they demonstrated this new PDK, process design kit, with the help of ILab guys actually. So they have tie up with them, and that's why they are very promising, because I would say they are very much promising because they will have the capability of integrating electronics and photonics in silicon on insulator. I think that silicon on insulator device layer thickness is around 165 nanometer or so. And also they have the technology for integrating photonics and electronics in bulk silicon also. So in that way, you don't need to use two different chip, something like this, for a FPGA application. Here you see the control electronics, control logic is a separate chip, and your FPGA is a separate chip you are considering. But with their technology, they can actually co-integrate. I think ILab is in a good position. I know that they are in a very good situation and they can do much better. I think they are coming like anything. I think, yeah.
So there are quite a bit of interesting questions. I hope you don't mind taking a few
Yes,
more.
sir. Please, please. Yeah.
Thanks.
If I can. Yeah.
So Deep Pal is asking like, what is the scope of silicon photonics for artificial intelligence?
Yep, I think, frankly speaking, I
More,
don't know much about artificial intelligence, but I see that a lot of review paper, and they are actually saying that artificial intelligence means you need a lot of switching network, right? Memory, switching network, all those type of things. And silicon photonics, actually CMOS technology, I think here I put down neural networks and artificial intelligence. Some papers are coming out, and they are, as as of now, they are predicting that that silicon photonics and some demonstration also lab level demonstration happening that this artificial intelligence, neural network, neuromorphic computation, all those type of things is possible in using silicon photonics, because it is just semiconductor foundry and CMOS technology and same technology. You don't need any additional infrastructure for manufacturing things. So it is going to come one day. Only thing is that people are calculating the cost effective or not. So it is just about to come, I'm sure. Yeah.
Right. Right. Thanks. There is a follow-up question from Rohin. This is something which I also wanted to ask. Like, so when we are integrating photonic and the electronic, circuits together or the technologies together, so won't there be additional silicon area, right, for modulation, waveguides, etc., and silicon photonics that adds to cost when integrated with CMOS? So IR Labs demonstrated on SOI 45 nanometer only.
Yeah. Yeah.
Right. So,
When the product will come with co-integrated things, right?
Mhm.
Electronics and photonics co-integrated product, when will come? That is the question, right?
No, I mean, there would be, I mean, how do you squeeze them, right? Like, so once you integrate photonics into it, like, so your waveguide dimensions are going to be
Oh, no.
diffraction limited,
Okay.
right?
So device layer, you mean to say, right? Adjusting device layer.
Yes.
Okay. So that is a good question.
Right.
That is a very good question. So you see, so far, you have a silicon photonics foundries. Mostly they are using 220 nanometer SOI. And most of the electronics foundries, they are using less than 100 nanometer. Okay, and they are going for their advanced technology node, 25 nanometer, less than that technology node they are going. Because of that, they need a thinner device layer. But for photonics, you cannot just go below 100 nanometer or 150 nanometer or something like that. So that's why Iron Labs, what they are doing, they are compromising. They have a very good PDK for RF SOI, so-called RF SOI. That RF SOI needed little bit of higher thickness of silicon on insulator layer. So that layer, it is actually 165 nanometer. This is little bit you are compromising with the electronics, little bit you are compromising with the photonics. So they have developed that 165 nanometer silicon on insulator layer for both electronics as well as photonics. So that is how they are gaining basically.
Right. Right.
So diffraction limitation, I think you compromise that device layer thickness is a little lower, means you are bent, you cannot tightly bend actually normally. That's a more side will be a little bit flat. That will be some compromise will be there.
Right. So Deepika has one question related to that. I'll can we cover this before asking Dr. Anuj Bhatnagar's question? Like, so what is the smallest ring resonator demonstrated so far?
I think so far I know that 5 micron worldwide, and in our lab we demonstrated 10 micron. But in our lab, though we demonstrated 10 micron, it's not yet optimized thing. Some loss is a bit high, but still with a 10 micron ring resonator, I think our student demonstrated a Q value in the order of about 9 into 10 to the 5, about 9 lakh. So, that is a very good quality ring resonator. We are exploring that for quantum applications actually.
Right.
But outside world, people demonstrated 5 micron, and they have demonstrated also circuit application.
Right. So, Dr. Anuj Bhatnagar, so is asking like, so what are the technological challenges silicon photonics is likely to face?
So, one major immediate challenge actually, the something like off-chip laser is a major bottleneck now, I think. So that is one thing. And another thing is that so far large scale integration, particularly for microphotonics and quantum photonics, people are using thermo-optic phase shifters. And that thermo-optic phase shifters, actually each phase shifter for 5 phase shift, they are reporting, also we have reported about 40 to 50 milliwatt power. And thermo-optic phase shifter means if you want certain bias, that means 50 milliwatt, that means constant power source is there. Okay, so you may need thousands of such power splitters phase shifters to operate large scale integrated like a FPGA, for example, if we just consider. So in that case, if you estimate the power consumption is going something like that, more than 25 watt, even 50 watt or something like that. So that is one thing we have to work on, how to reduce that instead of thermo optic phase shifters. Probably, as I said, that this phase change, phase shift memory, GST, IST, that type of material people are thinking. But that is also another problem, is that they are not CMOS compatible. That those type of materials you cannot use in the CMOS foundry. Whatever we do research in our university, also institute level, also we can use GST, IST, we can demonstrate. But ultimately that material should be accommodated in foundry for production purpose. So that is one major challenge, how to reduce the power consumption for large scale integrated circuits. And probably that is a huge area potential for our research scholars also to come up with a good solutions, I would say. And off-chip laser, as I said that, but people are trying to do some kind of, people tried many ways to integrate like silicon, germanium integration, everything for hybrid laser, etc. But they were not so efficient. And now people are trying flip chip bonding, get 3-5 semiconductor lasers and bonding directly. So heterogeneous integration. And that particular direction people are moving, but monolithic integration, that is also one challenge also. But all the product concern is constant. I think people are not bothering. Okay, laser can be outside, just fiber you can connect. That is what. But if it could be integrated together, then I think that would be a lot of cost will be reduced, production cost. Those are the challenge actually, I would say.
Thank you very much, Professor Vijay Das. Like, so you have really given a wonderfully,
Thank you very much.
compact
Okay.
talk in which, like, you have completely covered the history of silicon technology with photonics, where it came, how it came, and then what is the present status and future challenges. Like, really, I hope students will really gain from this talk, right? And
Yes.
I want to, at the end, like, I just want to take this opportunity to thank IIT Bombay Photonics chapter as well, the student chapter of
Yes.
IIT Bombay, right? So they're also actively participating in this. So thank you very much, all of you.
Thank you very much.
Thank you, Professor Das.
I'm really honored to present and also new chapter. I think I wish best of luck for the future. Yeah. Thank you very much.
Thank you.
Yeah.
Thank you.
Okay. Thank you. So